Today's lesson is over transformations of quadratic functions. We're going to talk about translations, reflections, and dilations. And first, I want to talk about vertex form of a quadratic. This is one of the equations or forms of a quadratic that I talked about in the previous lesson. And today's lesson works really well with transformations. Vertex form of a quadratic allows us to easily identify the vertex of a quadratic. We talked about that in the previous lesson. But it also allows us to see all the transformations from our parent quadratic function, which is f of x equals x squared. Remember that's that most basic quadratic function. So your vertex form is f of x equals a times x minus h squared plus k. And what do each of these letters represent? Well, that a value represents your vertical dilation, which is a stretch or compression, right? So am I making that quadratic narrower, like skinnier, or like wider, right? That h value, which is in purple right here, that represents your horizontal translation. Are you moving that quadratic left or right? That k value, which is in blue, represents your vertical translation. Are you moving that quadratic up or down? And your vertex, you may recall, is hk. All right, so let's move on to horizontal and vertical translations. And the first thing we're going to talk about is your vertical translation. So are you moving that quadratic up or down? So your vertical shift is the absolute value of k units. So that's just like a fancy schmancy way of writing, k, are you moving it up or down, that many units. So let's get into what really matters. A vertical translation will shift your entire graph, like every single point on your graph will move up or down. So let's look at your parent quadratic function, which is in black here. And then we've got another quadratic function that's been transformed. So we're calling it a different name. Instead of f of x, we're calling it h of x because it's a different function. And it's been transformed. H of x is x squared plus 2. So look at what happened to that vertex. It moved up 2 units, and then every point also moved up 2 units. So one of the things, and let me change colors here, that I like to talk about is on a quadratic function, from my vertex in the middle, I go out 1, up 1 in both directions. I go out 2, up 4 in both directions. I go out 3, up 9 in both directions. From that new vertex, you should still be going out 1, up 1, from that vertex, out 2, up 4. Let's see, out 2, up 1, 2, 3, 4, right here, right? And out 3, up 9. Let's look at this other transform function. Again, it's a different function than each of these other two functions, so we're giving it a different name. That name is g of x. G of x equals x squared minus 4. So we're going to take that vertex and we're going to move it 1, 2, 3, 4 units down. There's where my vertex is now. Every point gets moved, so from there it's out 1, up 1, out 2, up 4, out 3, up 9, and so on and so forth. So it affects our entire graph. So this moved our vertex down 4, this moved our vertex up 2, and every point moved correspondingly as well. So now let's move to horizontal translations, and they're a little bit trickier than your vertical translations. So in horizontal translation, just like vertical translations move your entire graph up or down, horizontal translations will shift your entire graph left or right. And I'm going to change colors here since we have purple in this graph. So when you're translating your function horizontally, I can write this fancy smancy horizontal shift of the absolute value of h units. That tells me that my function is going to move, every single point is going to move left or right. That many units. So if I have my parent function here, f of x equals x squared, I can denote it like this, f of x minus h, that would look like x minus h squared. So horizontal translations shift your entire graph left or right. So I'm given my parent function, which is in black right here. Your vertex is at 0, 0. This function right here, h of x, equals x plus 3 squared. What is the value, or let's first look at what happened to my function. Did it move left or right? It moved left 3 units. So I'm going to tell you where students struggle. They see that x plus 3 and they automatically think, oh, it's going to move right 3 units. That's not what happens. It's kind of like opposite world inside your parentheses with horizontal transformations. So this is actually going to move our function. Every single point is going to move left 3 units, which is why my vertex is not at 0, 0 anymore. It's at negative 3, 0. So what's the value of h? H is actually negative 3. So let's look at our other function over here, g of x in green. G of x equals x minus 6 squared. So what happened to my function? My vertex moved right 6 units. It's now at 6, 0 rather than 0, 0. So this function moved right 6 units, right? So what's the value of h? H equals positive 6. So let's move on. It's just kind of opposite world when you're talking about those horizontal translations, okay? So the next little section says, describe the transformations of f of x equals x squared for each function represented by j and g. So j of x equals x plus 2 squared minus 3. So what transformations happened? Well, you have, let me close that, a horizontal translation or shift, right? The entire function is shifted. How many units? 2 units to the left. So left 2. You've got a vertical translation down 3. That's what's happened to our parent function. Let's look at the next function. G of x equals x minus 8 squared plus 5. You have a horizontal translation, right 8. Then you have a vertical translation. Oh, whoops, I'm sorry. This should say down 3. You have a vertical translation, up 5. Okay, so that's what's happened to our parent function. And again, because it's in vertex form, we know, like for this function right here, because that entire graph moved right 8 and up 5, my vertex is now at positive 8, positive 5. For this j of x right here, because that entire function moved left 2 and down 3, my vertex is at negative 2, negative 3. So let's move on to our next section. Reflections in the axes. And let's first look at a reflection across the y-axis. Okay, so right here, the y-axis. So what happens when you're reflecting something across the y-axis? You get opposite x, right? It's opposite all of your x values. So if I have my parent function here, I can denote it like this, f of negative x, right? The opposite of x. So what is that going to look like? The opposite of x is I'm going to have that reflection in my parentheses. So negative x, oh my gosh, and this right here should actually be outside the parentheses. So that should look like this, negative x squared, which negative x squared is x squared, which is right there, okay? So that actually needs to be changed. So this right here, that parenthesis should be right there, okay? So negative x squared. So what happens to your graph? It flips across the y-axis. All x values become opposite. And as you can see, where is our parent function that I've got that should be graphed in black right here? It's not there. It's not there because it's underneath the reflected function across the y-axis. It's underneath that orange function, right? So actually what happens is y equals x squared is its own reflection in the y-axis. So let's write that down. Y equals x squared is its own reflection in the y-axis. Let's move on to reflection across the x-axis. When I have a reflection, and I'm going to highlight this, across the x-axis, that's going to be opposite y, right? I'm flipping it down, okay? So here's my parent function, f of x equals x squared. Reflection across the x-axis, that's opposite y. So my like negative sign goes out in front of that negative f of x, and that's just how I denote it, equals, and that looks like this. Notice, and I did the same thing over here. That negative sign is outside the parentheses. This parentheses should be right there. It should look like this. Negative x squared. Okay? So the opposite of x squared, which should be negative x squared. Okay, so I've got to change that. And right here, so it should look like this. F of x, that equals negative x squared. Okay, so you have that negative sign out in front, which means it's going to flip and open down. Your vertex is a maximum, not a minimum anymore. So what ends up happening? Here's f of x equals x squared. My vertex is at 0, 0. When I flip it, notice that nothing happens to my vertex in either of these. But instead of going out 1, up 1 in both directions, it goes out 1, down 1. Out 2, down 4, right? Out 3, down 9. So that's that transform function that's graphed in pink. And let's move on to describe the transformations of f of x equals x squared for each function represented by h and m. H of x equals negative x plus 1 squared. What happened? That's a horizontal translation. Left 1. And then what else happened? I've got that negative out in front. That's a reflection across the x-axis. And then in our next function, we have m of x. And notice that that's just like another name for a function, right? It's a different function, so I've given it a different name. M of x equals negative x squared, and I actually wrote that right on this one, right? So that 2 exponent is on the outside of those parentheses, minus 2. So first off, that is a vertical translation down 2. Vertical translation down 2, and it's also a reflection across the y-axis. A reflection across the y-axis, right? Because it's opposite x, right there, it's opposite x, then that's a reflection across the y-axis. When my negative is out here, outside the parentheses, that is opposite y, which is a reflection across the x-axis. So let's move on to our next set of transformations, which are stretches and compressions. So vertical stretches and compressions are, I think, easier to understand for students. These vertical stretches and compressions are denoted like this. If I have f of x equals x squared, I'll put an a out in front, or a number out in front, and that a affects the y values. It affects the y values. So what happens? So I've got the parent function that is graphed in black, right? Vertex at 0, 0, out 1, up 1, out 2, up 4, and so on and so forth. H of x is graphed in blue. I've got an a value that's greater than 1, so 2x squared. What ends up happening? What happens is I take that x value, let's say I plug in 1 for x instead of out 1, up 1. I'm going to multiply that, what would be that y value, by 2. So I'm going to go out 1, up 2. Instead of out 2, up 4, I'm going to go out 2, up 8. I'm going to double it. All of my y values get doubled. So what ends up happening? It's a vertical stretch. So the y values stretch by a factor of 2. And let's write that down. The y values stretch by a factor of 2. If I look at the graph that is in red, g of x equals 1/2 x squared, well, instead of doubling all of my y values, what ends up happening? I'm going to half them. So instead of out 1, up 1, I'm going to go out 1, up 1/2. Instead of out 2, up 4, I'm going to go out 2, up 2. Right? Instead of out 3, up 9, I'm going to go out 3, up 4.5. So what ends up happening? That's a vertical compression, right? I've got, and it's going to make it wider, right? It doesn't make that parabola narrower, it makes it wider. Okay, so let's go ahead and write, or down here, let's write that the y values compress by a factor of 1/2. So your y values compress by a factor of 1/2. And down here, I've got a little blurb that says it's a vertical stretch when a is greater than 0. It's a vertical compression when a is greater than 0 and less than 1. So if I've got like a fraction or a decimal in there, right? Like a proper fraction and a decimal like less than 1, then that's a vertical compression. And now let's move on to your horizontal dilations, which we call your horizontal stretches and compressions. And talking about horizontal stretches and compressions, if I start with my parent function, f of x equals x squared, I can denote it f of a times x equals ax squared. So where's the a value? It's inside the parentheses. I'm going to multiply that a value times x first. Then I'm going to square it. So let's look at, first in graphed in black is our parent function, f of x equals x squared. And of course, every single one of these is f of x, but let's call this g of x and let's call this h of x. So when we look at the function that's graphed in green, that's g of x, and that's g of x equals 2 times x squared. So the first thing I'm going to do is multiply that x value times 2, then I'm going to square that. All right? So what ends up happening? Let's think about this. If I plug in an x value of 1 right here, 1 times 2 is 2, 2 squared is 4. Okay, and the same thing would happen if I plugged in a negative value, right? Because if I square a positive or a negative, I'm going to get a positive value. If I plug in 2 for x, I'm going to multiply that x value by 2. 2 times 2 is 4. 4 squared is 16. So that's like off the graph, right? So what does it look like? It almost looks like a vertical stretch, but we actually call this a compression. So here's what's confusing is like the wording around this. But if you just, I'm going to give you the wording, but just remember that it's kind of like opposite world when we're talking about horizontal transformations, right? Those translations are kind of tricky, and these stretches and compressions are kind of tricky. So the first thing I want to tell you is that this affects it by a factor of 1 over a. So it affects by a factor of 1 over a. And right here with this function that we've got in green, oh my gosh, there's too many arrows. Let me erase some. And, okay, this right here, I would write this, that it is compressed. So it looks like a stretch, right? A vertical stretch, but this is actually horizontal, right? So I'm going to call this a horizontal compression. It's compressed toward the y-axis. So it's compressed toward the y-axis by a factor of 1 over 2. So now let's look at this h of x, which is like graphed in purple. H of x equals 1/2 x squared, right? So that 1/2 is inside my parentheses. And it looks wider, right? So let's plug in something like 2, right? If I plug in 2 for x. If I plug in 2 for x, I take half of it, 1, and then I square it, and I get 1. So 2, 1 is a point, and negative 2, 1 is also going to be a point on my graph. So it looks like a vertical compression, right? But how actually do we say this correctly? This is actually a horizontal stretch, and it's stretched away from the y-axis by a factor of 2. It's stretched away from the y-axis by a factor of 2. Okay, so I've got some like just stuff down here that you can refer to. It affects it by a factor of 1 over a. It's a stretch when a is between 0 and 1. It's a compression when a is greater than 1. And let's move on to some practice problems down here. And I'm going to go fairly quickly through this, hopefully. I know these lessons are long. This says describe the transformations of f of x equals x squared for each function, then graph the transform function on the coordinate plane. So let's first describe the transformations that took place. I really like to talk about the horizontal and vertical translations first, because that lets me know where my vertex is. So I know that it's going to move left 8 and down 6. Left 8 and down 6 tells me that my vertex is left 8, down 1, 2, 3, 4, 5, 6. That's where my vertex is, right? This negative out front tells me that it's a reflection across what? Which axis? It's a reflection across the x-axis. So instead of opening up, it's going to open down. There's no stretch or compression, so from that vertex, I know it's going to go out 1, down 1, out 2, down 4, right? There's my pattern. And it opens down. Let's look at h of x, number 2. Negative x inside the parentheses squared plus 2. So first let's talk about the vertex. There's no horizontal translation, but that plus 2 tells me that this is going to move up 2. My vertex is now at 0, 2. It's not a reflection across the x-axis. That negative is inside the parentheses. This is a reflection across the y-axis. So what ends up happening with that? Nothing. It looks the same, right? It's its own reflection. So I'm going to go out 1, up 1, out 2, up 1, 2, 3, 4, and I'm just going to leave it at that and graph it just like that. And it's not super pretty, but it looks like that. And let's move on to the next two. Number 3. There's a lot going on with this one. J of x equals 4 times x plus 2 squared minus 6. So let's first talk about the horizontal and vertical translations. This right here tells me that my function is going to move left 2 and down 6. So let's write that down. Left 2 and down 6. Left 2, down 1, 2, 3, 4, 5, 6. This 4, whoops, let me move it down a little bit. This 4 that's outside the parentheses is a vertical stretch by a factor of, 4. So I know there's no reflection or anything, so this function is going to open up, right? That vertex is going to be a minimum value. But because I've got a vertical stretch going on, instead of going out 1, up 1, I'm now going to stretch that, and I'm going to go out 1, up 1, 2, 3, 4. And instead of out 2, up 4, those y values are going to be stretched by a factor of 4. So it would go out 2, up 16. Well, that's going to be, actually, I think that's all the way up here. If I were to 10, and then that's down 6, so it's actually going to be right here. Whoop, it's my y-intercept right there. And then this one's going to be over here, right? Because it's like a mirror image from that axis of symmetry, right there. Oh my gosh, that's like terrible. Let me just erase this. We're just going to not write that because that was just really bad. Okay. And okay, so now when I graph it, I've got this like super narrow parabola right here. Okay, moving on, and I think this is our last one. P of x equals 1/4 x squared. So the only thing I've got going on here is that it's a horizontal stretch, right? How do we call it if we really want to get like technical? If you're like, I don't know what it is, just call it a dilation, right? It's a horizontal stretch by a factor of, well, 1 over a would be 1 divided by 1/4, which would be 4. Okay, so I'm not moving left or right. My vertex stays at 0, 0. But let's think about this, okay? I'm actually going to plug in the first x value that I'm going to graph is when x is 4. If I plug in 4 for x right here, 1/4 times 4 is 1. 1 squared is 1. So 1, 2, 3, 4. 1 is my first point, and negative 1, 2, 3, 4, right? Negative 4, 1 is the first point that I am going to graph. And then the next point that I'm going to plug in, let's plug in 8, right? That's a really nice number because I know 4 is a factor of 8. So if I plug in my next x value to be 8, and I do 1/4 times 8, well, that's 2. And 2 squared is 4. So my next value is going to be 8. 1, 2, 3, 4. 8, negative 8, also 4, right? So my function is going to look like, oh my gosh, whatever. It's going to look something like that, all right? Then we call that a horizontal stretch by a factor of 4. And that concludes your notes over quadratic transformations. I hope it was helpful.